Last time we learned how constitutive laws related forces to variables describing components, but what principles do we use to combine those constitutive laws into models of mechanical systems? Newton's laws provide the basis for everything we do. You probably know Newton's laws already. They say that the sum of forces at a point must be equal to the mass of that point times its acceleration. Something we often do not acknowledge is that Newton's laws are really only interesting or deep if there are multiple forces involved. That is, the statement that F equals ma is not all that interesting because, of course, the second derivative of position must be equal to something. But the sum of forces being equal to mass times acceleration is very deep because that means that there can be multiple components that all interact with each other through this magical relationship. As an example, let's go back to our spring and damper system. Again, we have a wall on the left, and we have a spring and a damper, and the spring and damper are in parallel with an external force acting on them. We're going to assume that that external force is equal to 0. This spring-damper system could represent a shock absorber on a vehicle that has a load of an external force on it, or a bungee cord like this one that I can stretch by pulling on the end with an external force. Newton's laws tell us that the sum of forces at the point where the spring and the damper meet must be equal to the mass times acceleration of that point. A positive external force will cause the point to accelerate to the right. On the other hand, a positive spring force, indicating that the spring is in extension, will accelerate the point to the left. Similarly, a positive damping force would act to the left. Hence, the sign convention we chose for the individual mechanical elements have consequences for the signs in Newton's equations. The external force has a positive sign, but the spring force and the damping force both have negative signs, and adding all of those together must be equal to the mass times acceleration. I strongly recommend that you get in the habit of making sure that you think about the physical meaning of each force as you incorporate it into Newton's laws. Now, if we assume that the external force is 0, and if we assume that the mass is 0, we are left with a much simpler expression of Newton's laws. If we use the constitutive laws from Lecture 2 that relate the spring force to the spring position and the damper force to the damper velocity, so here we have F sub s is equal to k times x sub s, and F sub d is equal to b times v sub d. And we know that F external is equal to 0, and we know that m is equal to 0. So that means that minus F sub s minus F sub d is equal to 0. We can substitute these constitutive relations into Newton's laws, and we get an equation involving x sub s and an x sub d. If we additionally keep in mind that the time derivative of the position of the spring is equal to the velocity of the damper, we get a simple equation involving only the position of the spring. Now, if we define x to be the position of the spring, just dropping the s, and solve for x dot, remembering that the dot notation is the same as d dt of x, we get a differential equation, x dot is equal to minus k over b times x. This is called an ordinary differential equation, or ODE for short. This ODE says that the derivative of the position is equal to minus k divided by b times the position. Note that this means that the derivative of the variable x is equal to a function of the variable x. This is the form of an ODE. d dt of something is equal to a function of that something. In this case, that something is the position x, and f of x is equal to minus k over b times x. In general, the something is called the state of the ODE. States of mechanical systems do not have to be positions. Later, we will also use velocity of masses as states. Engineers get good at choosing the state of an ODE with experience, and you will get good at this as well. In principle, an ODE can be very complex. For instance, it could look something like this. We could have x dot is equal to some horrible function that's a function of x. This is clearly a huge mess, but for us, we will always focus on what are called linear, constant coefficient, first-order ordinary differential equations. Linear means that the dependence of a state velocity on a state is always a line. Constant coefficient means that the slope of that line is always a constant. First order means that there is only one time derivative. That is, we should only expect to see one dot over x. Let's finish with another example and go back to the model of the spring and damper, but now allow the external force to be non-zero. This would mean that we would have F external minus F sub s minus F sub d is all equal to 0. If we substitute in the constitutive laws, we get F external minus K x sub s minus B V sub d, where we know that V sub d is equal to x sub s dot. If we then solve the differential equation by looking at x dot, we get x sub s dot is equal to minus k over b x sub s plus f external over b. This would be like how we take a bungee cord and pull on it with constant force. Now we have the external force in the equation, but the mass is still 0. If we replace the spring and damper forces by their constitutive laws, we can solve for an ordinary differential equation that now includes the external force. It is worth thinking about this differential equation and what it means. It says that if the position of the spring starts out less than 0, making the left-hand term greater than 0, and if the external force is greater than 0, then the velocity of the position of the spring must be positive. If the position of the spring is positive and the external force is negative, then the velocity of the spring must be negative. But if both position and force are positive, we don't know which direction the spring will move. It depends on the magnitude of the external force, the spring constant k, and the damping constant b. The most important thing from today is to remember that Newton's laws lead to ordinary differential equations, and that if the constitutive laws are linear, you should expect a linear, constant coefficient differential equation.